Let's talk about trapezoids, which are kind of different than everything we've talked about in the previous few lessons because trapezoids are not parallelograms. A trapezoid is a quadrilateral with exactly one pair of parallel sides, and that's contradictory to the definition of parallelogram, which is that it's a quadrilateral with two pairs of parallel sides. So all of the stuff that we've learned about parallelograms is not true for trapezoids. Trapezoids get all of their own sets of characteristics because trapezoids are not parallelograms. All we know about trapezoids is that they have exactly one pair of opposite sides that are parallel. But we can add some extra information onto that. Because we have two parallel lines, we must have consecutive interior angles. So trapezoids also have two pairs of consecutive angles that are supplementary to each other. Those are the consecutive interior angles created by the parallel lines and the non-parallel sides of the trapezoid. But we do also have a special kind of trapezoid that has a little bit of extra information with it, and that's called an isosceles trapezoid. You might remember the word isosceles from our triangles unit. Isosceles triangles are ones that have two congruent sides, and it's the same idea with isosceles trapezoids. If you have a trapezoid whose non-parallel sides are congruent to each other, then it's considered isosceles. It's important to note that if you have the parallel sides are the ones that are congruent to each other, that actually makes it a parallelogram. We learned that all the way back in the parallelograms video. It was just called the parallel and congruent theorem. If you have a quadrilateral that has a pair of sides that are both parallel and congruent, then it's a parallelogram. So be careful, make sure that the sides that are congruent are the not parallel sides. But if you have this kind of a situation, that it's a trapezoid with two congruent sides, then it has base angles that are congruent to each other. You probably also remember the term base angles from our triangles unit. The base angles are the ones that are attached to the base. And in this case, we actually have two bases. The bases are the ones that are parallel to each other. So angle A and angle B are base angles because they're both attached to one of the parallel sides. And angle D and angle C are the other pair of base angles because they're attached to the other base, the other parallel side. So if it's isosceles, if these two sides are congruent to each other, then the base angles have to be congruent. You can also use the converse of this to prove that something is a isosceles trapezoid. If you can show that it has one pair of parallel sides and that the base angles, each pair of base angles are congruent, then you could conclude that AD and BC are congruent. Additionally, if it's isosceles, then you know that the diagonals are congruent to each other. So if it's a trapezoid and AD is congruent to BC, then you would also know that AC is congruent to BD. The diagonals would have to be congruent. However, remember that this is not a parallelogram. So we do not know that the diagonals bisect each other. In fact, they do not bisect each other. So this little chunk of this diagonal is not congruent to the other chunk of that diagonal. If we were to call this point E, AE is not congruent to CE. We do not know that the diagonals cut each other in half. We only know that the diagonals are congruent to each other, and we only know that if it's an isosceles trapezoid. If it's a normal trapezoid, that's not true. But what is true for all trapezoids is midsegments. You probably remember the word midsegment from earlier this year as well. A midsegment is a segment that connects the midpoints of sides of a shape. So for example, M is the midpoint of side AD because DM and AM are congruent, and S is the midpoint of BC because BS and CS are congruent. MS is the segment that connects those two midpoints, so it's called a midsegment. And what we know about midsegments of a trapezoid, it could be isosceles or it could be non-isosceles, that doesn't matter. But a midsegment of a trapezoid will always be parallel to both of the bases. So all three of these lines are actually parallel to each other. And we actually know that the length of the midsegment is the average of the bases. So if you add AB and DC and divide it by 2, or take half of it, that finds you the average, so MS would be equal to the average of the length of the top base and the bottom base. So let's put all of that information together and answer each of these questions. Which line is JK parallel to? Well, JK has to be parallel to ML by the definition of trapezoid, but it would also have to be parallel to the midsegment, so it's also parallel to XY because of the midsegment of a trapezoid theorem. What about angle J? Angle J has to be supplementary to angle M because of the consecutive interior angles theorem. Since JK is parallel to ML, these two angles have to be supplementary to each other because they're consecutive, they're on the same side of the transversal, and they're interior, they're in between the two parallel lines. That's just the consecutive interior angles theorem from first semester. What about KL? What is it congruent to? That's actually a trick question. We don't know that KL is congruent to anything. We weren't told that this is an isosceles trapezoid, so you cannot assume that KL is congruent to JM. And like we already said, XY is parallel to JK and ML. That's the midsegment of a trapezoid theorem. But what about JX? What is JX congruent to? Well, JX has to be congruent to XM because of the midsegment of a trapezoid theorem as well. That has nothing to do with whether the trapezoid was isosceles or not. Midsegments always connect the midpoints of the opposite sides of the trapezoid, regardless of whether those opposite sides are congruent or not. So JX has to be congruent to MX, and LY has to be congruent to YK because of the midsegment of a trapezoid theorem. What we don't know is whether all four of those segments are congruent to each other. If this is isosceles, then yeah, all four of those little segments would be the same. But since we're not told that this is isosceles, we don't know that all four are the same. We only know that JX is congruent to XM and that KY is congruent to LY. Our next trapezoid is isosceles though. EFGH is an isosceles trapezoid. So HG would have to be parallel to, well, EF, that's just the definition of normal trapezoid. But this time we can say that EH is congruent to FG because of the definition of isosceles trapezoid. Those are the two non-parallel sides, and if it's isosceles, then they have to be congruent. And since it's isosceles, we also know the diagonals are congruent, so diagonal EG would have to be congruent to diagonal FH. So let's talk about the angles. Angle EFG, or you could just call it angle F, has to be congruent to angle E, or angle FEH. And that's the base angles of an isosceles trapezoid theorem. Since these sides are congruent, it's isosceles. Since it's isosceles, the base angles must be congruent to each other. Angle EFG, or angle F, again, so same starting point, but instead of talking about congruent, let's talk about supplementary. That angle would have to be supplementary to angle G, angle HGF, and that's the consecutive interior angles theorem. Okay, well, how long is MS? Well, we don't know any numbers, so we're just going to have to represent this with the side lengths. MS is the midsegment, and the midsegment is equal to the average of the bases. In other words, you take 1/2 of the sum of EF and HG. So let's actually do a problem where we calculate the length of that midsegment. MN must be the midsegment of this trapezoid because M is the midpoint of PS, because PM and SM are congruent. And N is the midpoint of QR because QN and RN are congruent. By the way, you can identify that this is not an isosceles trapezoid because these two sides are marked with different segment markings than these two sides. But that doesn't matter for the midsegment. The midsegment will always just be the average of the bases. So A would be equal to 1/2 of 23 and 31. So 1/2 of 54, A must be 27 kilometers. Okay, let's calculate the angles. B and C are what we're looking for, but since this is not isosceles, we don't know that B and C are the same. Instead, we're going to use these two angles, adding up to 180, because they're consecutive interior angles, to solve for B, and use the same reasoning to say 125 plus C equals 180, and figure out that C must be 55 degrees. So in fact, we have just proven that this is not an isosceles trapezoid, because my base angles are different from each other. As opposed to our next diagram where we're given an isosceles trapezoid, and I drew it like this on purpose to make you uncomfortable because we're so used to seeing trapezoids sitting on their base, but base does not mean bottom, so don't think that 18 is the base just because that's the side that this shape is sitting on. The bases are the sides that are parallel. So EH and FG are the bases. Those are the parallel sides. And since it's isosceles, the non-parallel sides must be congruent to each other. So W would have to be 18 feet. The base angles are congruent to each other if it's isosceles, and the base angles are the ones that are both attached to the same base. So angle E and angle H are a pair of base angles because they're both attached to this parallel side, EH. And likewise, angle F and angle G are a pair of base angles because they're attached to the other base, the other parallel side. So I could say that X is equal to 62 degrees because of the base angles of a trapezoid theorem. I could then conclude that Y is 118 degrees because of the consecutive interior angles theorem. These two angles are consecutive interior angles, which means they have to add up to 180. And then I could conclude that Z is 118 because of the base angles of a trapezoid theorem. And that's all you need to know about trapezoids and isosceles trapezoids. In our next video, we're going to put everything all together and see if we can use all of the properties of things that we've learned so far to solve for missing angles and side lengths.